Okay, so let's jump into hash functions, and first the definition of hash functions. Hash functions are auxiliary function, which translates into Hilfsfunktion. You know, it's not like a block cipher, something used for encryption. So you always use hash functions in conjunction, typically together with some other cryptographic mechanism, but it's a super important one. Okay, hash functions are auxiliary functions. In cryptography, period, they are used e.g., for example, for signatures, you know, this is what we are doing today here. MACs, message authentication codes, is something we're going to introduce in 2 weeks. Don't worry if you don't know what I'm talking about. Key derivation. Schlüsselableitung. Again, this is stuff we do towards the end of the course. RNGs. Anybody remember what RNGs are? We did that in the 3rd or 4th week. That stands for sehr gut, random number generators. Blah, 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 blah. So we use them. Essentially what I'm trying to say here, as soon as you have a real-world crypto implementation, there's a very high chance you're going to end up using hash functions. Okay. The way I motivate them, and some other books do that, and I think it's an excellent way, is to motivate them over digital signatures, which is maybe the historical main application for them. Okay. So let's look at a motivation. We look at digital signatures, okay, and I just do the beginning of the protocol. Exactly the stuff we did the last 2 weeks. So we have Alice and Bob. Alice starts with distributing his public key. Then he has a signature function, whatever that is, you know, to sign his email. X using his private key. And then he sends message X and signature S over the channel, and Alice verifies blah, 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 blah. Now let's drill a little bit into the details. What happens here, the signature? How does this look in the real world? If we use RSA at this point, the digital signature algorithm tells us to compute S as x to the d mod n, one exponentiation, right? We're already on board, very easy so far. Very easy question. What is the problem now if I give you no, you give me, you want to send a PDF file to me by email, attachment, right? PDF file, you want to sign it this way. Where's the problem here? Why? Well, what is the real world problem if you have a PDF file and you want to do that operation here? We have 90 minutes, so take your time with the answer. What's the problem here? Yeah.
Yeah, you have to create a signature for every block we send.
Yeah, for every block we send. How long is n there? N is maybe 2,000 bits, 2,048 bits. This is 256 bytes. This is short. Most PDF files are longer, right? What you see there with this algorithm, this formula, you can only sign something like 256 bytes at a time. Typically, your messages are longer. Okay, this is a problem. X is restricted in length, e.g. X is shorter than 256 bytes, okay? This is pretty annoying. So what do we do? Let's say we have a message of 1 kilobyte. So let's say 4 times this length. What would we do? Probably the ad hoc approach for signing is the following. Going to blow that up further. It's exactly what you see here in this figure. Okay, so this is probably what most people would think this is how we can deal with the problem. We have a longer message, let's say consisting of 4 blocks. We want to sign that, so what we do, we chop the message in 4 blocks. 1, 2, 3, here I have n, let's say in 4 blocks, and each block is individually signed. Voila, that's it. This is kind of what we do with block ciphers, right? AES only encrypts 128 bits, so we do chunks. If you read the caption, die Bildunterschrift, at the very bottom it says insecure approach to signing of long messages. So what you see there is wrong, is really bad, okay? And now I want to discuss with you why, and what I do in the book, I list 3 reasons why that is a really stupid idea, what we do then. Does anyone have any ideas without looking in the book? What is one practical problem with doing this approach here? Very practical, very engineering, yeah? It's not practical, but it's good. So he says you can simply austauschen, exchange a block. So one problem, that's actually the most serious one, that's a good comment. One thing what happens here is, let's say X, this is a contract. X is a long contract, right? And at the end, there might be attachments, Anhänge, and sometimes the attachments are really important, right? They talk about the evaluation of a company or a house or some other financial aspects, and that might be in the Anhang, in the attachment. So what you can do, for instance, here, you drop, as an attacker, you drop XN and SN, right? You just don't, interrupt the channel, you don't forward that. And so suddenly you have a signature, but the signature only goes over part of the message. Or maybe you have some signature in the middle and you just pull that out, okay? You can play that game further. You could also exchange messages, for instance, right? You could reorder. I don't know whether that makes sense, depends on the attack, but maybe, X2 and S2 could be exchanged with X3 and S3, okay? So what really happens is similar to this attack against the electronic codebook mode that we had last semester. This is secure. That means the signature works. You have integrity, non-repudiation, blah, 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 but only on the block level. But here you don't treat the message as one big message, but as n individual message. This is not good. So very good. So security-wise, this is already bad. Can anybody come up with another reason? Why? Practical reason? Ja.
Ja, man hat ziemlich viel zu verschlüsseln.
Ja, man hat ziemlich viel zu verschlüsseln. It's a lot of work. Remember, this is one of this really bad, for instance, RSA exponentiation. So what you have here, if you have a long message of let's say 1 megabyte or so, you have a few thousand, or let's say 256 megabytes. This is not gigantic nowadays, right? But we can only sign 256 bytes at a time. If you have 256 megabytes, it means we have to do, n would be 1 million. That means you have to do 1 million RSA exponentiation to do one stupid signature, okay? What this really means, what we suddenly have to do, we have to use public key algorithm, asymmetric cryptography, and run our whole message through an asymmetric algorithm. This is bad, okay? That would be really, really slow. So there's another reason why we don't want to do this approach. First, it's unsecure, and then it's really slow. Okay, so forget it. Yeah. Okay, we're not doing it this way here. Okay, and that's a third reason. Or the other thing is message overhead. I don't want to go into that. Okay, so there are at least 2 reasons why this is really stupid. Okay, so the question is, what else to do, and the answer to what else to do is we use hash functions, okay? The solution to this problem is somehow compress the message X prior to signing. Means before we want to sign that, we try to compress it to make it smaller. Okay, so what would that give us? So instead of doing the stupid thing here, I just told you don't do what you see on this drawing there, on that figure. What we would like to do is, and this is actually a very, very important picture for the rest of today, maybe for the rest of your life if you stay in IT security. So what we do with x1 to xn, this really long message, 256-byte PDF file, you feed that in some kind of function, h, the hash function. What you get out is hopefully short enough so that you can feed that into the signature operation. And again, signature is RSA, something very arithmetically intensive, long operands, square and multiply algorithm, blah, blah, blah. So this is slow, but you only do that on a short output here. You do only do that once. This is what it boils down to, and the output is S. So this is what we're trying to do. Okay, this picture is today. This is a lecture today and actually next week as well. Okay. So, designing, what is it, figure 11.2. Okay, so this is what we're trying to achieve. And we do it, today is kind of a nice lecture, it's very constructive. Sometimes I come in, I give you an algorithm, and then we talk a little bit about how it works, and sometimes I explain you why we do things a certain way. Here it's very constructive. It's a very systematic way how we approach hash functions. We are at this picture at this moment, and now we derive requirements just by looking at this picture without going into bit shifting and other arithmetic properties or so forth. Before we talk more about H, let's look at a protocol that we get. This is basic protocol for digital signatures with hash functions. Okay, if I do w/v/, that means with. So we do kind of a modification of the protocol you see there. Bob sends kpublic over, and now instead of signing X directly, because again X is 256 megabytes, we compute something very nice and short, which we call Z here, Z, which is H of X, which is a picture there. Okay, you compress it, compress in quotation mark. So you get something nice and short out, and this nice and short hash output can then be signed using the private key. What you send over is the, as before, you send over message and signature, nothing changes. Alice verifies using Bob's private key. What are the inputs for the verification algorithm? Obviously S. What is the other input? What do we have to feed into the... What? Sehr gut. What is the other input for the verification function? Yeah. Z, exactly. So, very important. We signed that here, right? So we have to verify that, okay? In particular, neither at the signing side nor at the verifying side, the message is directly involved anymore, okay? So one practical question, how does Alice know what Z is here? What does she do? How does she get Z here? Z value. Yeah. She has a hash function. She goes in a bookstore, buys my book, and looks how age is being computed. She goes to Wikipedia, right? So she recomputes the hash and uses that as the input here. Okay, so that's it. Again, we're going to be in trouble. This is why the lecture is longer than 15 minutes today, because here and here we're not using the message anymore, right? And that might be an opening for an attack. And it is an opening for an attack. Okay? And of course the output of the verification process is go or no go, right? True or false, 0 or 1, right? It's a valid signature or an invalid signature. Okay? So this value Z is a fingerprint of the message of X, or a, in quotation mark, message digest. Wieso die Essenz? I don't have a good German word for that, okay? Die Essenz einer Nachricht vielleicht. Okay, fingerprint is pretty good, okay? So far so good. So that was the motivation. We're done with chapter 1 of today. And now we turn to the second chapter. Oh, I have one announcement to make in German. Wahrscheinlich sind wir heute ein bisschen früher fertig. Danach gibt es eine wissenschaftliche Umfrage von einer Kollegin hier. Wäre super, super nett, wenn Sie alle noch ungefähr eine Viertelstunde hier bleiben danach. Ist eine spannende Sache, ja? Okay, wir probieren so kurz nach halb Schluss zu machen, ja? Fände ich super nett. Danke. So, Requirements. For hash functions, okay? And we start, which we rarely do, really kind of a to-do list, what would be nice to have in an algorithm. Again, normally we do it the other way around. I give you an algorithm and then we discuss it. Now we try to really come up with, we do requirement engineering, okay? So the first requirement is, why did we get into this mess? Because why did we introduce hash functions here? Because we have real problems. Können wir ruhig sein? Hallo. Da auch. Da, Sie. Ja, genau, die Dame. Sehr gut. We got into this problem because the message, we can't sign long messages. So probably one of the first requirement is no constraints with the length, no Beschränkungen. Okay, so the first thing, and we write that explicitly down, is we would like to have arbitrary input length. Okay, so we don't want to construct a hash function that works with 256 megabytes, but if you have 260 megabytes, it doesn't work anymore, and we have to do again some block size stupid thing. We want to just have a function that works with any bit length. You know, whether we have a short email maybe consisting of 10 bytes or something of, and this actually happens, you compute a hash over your hard disk, right? 50 gigabytes. We only want to have one function. We always want to do this type of operation here, okay? That was the input. Then at the output, what we saw, the only thing that we can sign very well with standard algorithms is something like a few hundred bits, really. So what we would like to have in order to be able to always sign is fixed, short output length. Okay. So again, this is essentially, look at this picture, and these are, you know, the requirements we have. Okay. One problem we saw before, you know, when we looked at this naive approach, one problem, and one of you said it, it's, you know, fancy term is high computationally load, means this is really slow. Okay, if you do that with, you know, if you do compute an individual signature. We don't want to do that, but what's happening here, if you have a 50 gigabyte hard disk, you want to hash that, you have to feed all bits, all the, you know, 50 billion, 50 Millionen, no, Milliarden, 50, what is it? Trillion, right? 50 trillion bits in this function. You don't want to wait a week, right? So the third requirement is it should be fast, okay? And rather than fast, we call that efficient, but we really mean fast in hardware and software, blah, 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 okay? So this was easy, okay? What you will see now there are two more requirements, and they have to do with the security, and this is really the fun part of the lecture. Okay, this is really, really interesting. Okay, what's coming now. And we talk probably much more about attacks than we normally do when we discuss crypto algorithms. Okay. The first one I just give you without a big motivation, which is called Preimage Resistance. Oh, I'll show you. I'll show you the requirements. Okay. Maybe let's talk about this first. There are all good pictures in the book here. Okay. So one thing, what we would like to have with hash function is the following. This is kind of the first two requirements. Even if I have kind of a longish text here, there's actually the beginning of Alice in Wonderland here. If I feed that into the hash function, I get a fixed output. If I have a different input, I still have a fixed output, right? The output length is always the same, right? In this case here, it's 8 hex characters, 32 bits, okay? What is also important here is I'm not a crook, ich bin kein Betrüger, and then I'm not a cook, which looks almost the same, almost sounds the same. What is important, what I'm trying to convey with this picture here, if you look at this output and this output, the output should completely change. Okay? This is should be very sensitive. You know, one bit flip in the beginning, you should get something completely different out. Okay, so this is a little bit, you know, the first three requirements, a little bit security. So now comes this point 4, 5, and 6, which are called preimage resistance, second preimage resistance, and collision resistance. Okay, and this, again, we're going to talk about that for a while. So preimage resistance, or one-wayness, that means it's a one-way function. Okay, meaning what you see, what I'm trying to say, if I give you the hash output, it should be impossible to go back. Okay? If I give you the hash output, it should be impossible to compute x. Which is actually, and I have some kind of an example why that is important in the book, but it's, for digital signatures, it's probably not that super important, but for many other applications, such as key derivations, this is very, very important. So you want to have a one-way function. Okay? This is what you see there on the left-hand side. Then the second one is called second preimage resistance. Oh, preimage, this is a term I hate because it's far too complicated. What they mean with preimage is input. Okay? Das Vorbild, ne? Vor in, but not like this idol, but the previous image or the input image. Okay? So second preimage resistance, what that means is what you see here. Given is x1 and the output, and now an attacker should not be able to compute x2 with the same hash value. Okay? And why is that important? Second preimage resistance. Let's discuss it a little bit. Second preimage attack. Okay. Assume the first message is transfer €10 in Oscar's account. Let's say this is a message that Bob is sending, right? You know, she's transferring €10. He's sending that to his bank, and it's digitally signed, so it's coming from Bob. So now for Oscar, if Oscar wiretaps, it would be very interesting for Oscar to change the €10 into 10,000 euros, right? Okay. So what happens if Oscar can actually do that? Oh, and let's say this is true, and I mean, coming up with this ASCII characters is easy, right? But there's this additional condition that x1 and x2 have the same hash output, the same hash value, the same z. Okay. So let's say we do that. And Bob has x1. x1 means €10. It's a 10 euro bank transfer. 10 Euro Banküberweisung, right? Now Oscar, bad guy, right? Hacking somehow in the internet backbone. What he's doing here is he replaces that message by x2, S. Okay? This is 10,000 euros. That's a faked one, right? So what happens here, and of course it's not red. You know, he's not using red chalk for doing that, right? That means it doesn't say, hey, I'm a faked message. It still says, hey, I'm a message coming from Bob, right? So Alice, being the bank, she doesn't know this is fake. So what she does, she hashes x2 here. And now the problem, because it's the same z value, that means the verification still checks out here at this point. Okay? You just learned something very, very important here. Okay? This is what I stressed before. Both the signing operates on that and the verification operates on that. They're not operating on the message. So if you now somehow, try to sneak the wrong Z value in here, you use one message here and a different message at this point here, you might succeed. Okay? This is the price you pay when you fiddle around with hash functions, right? So this is obviously something we want to avoid. We want to have second pre-image resistance. So somehow we want to build hash functions where this attack doesn't work. Okay? What it boils down to, also am Ende, Endresümee ist, that Oscar should not be able to find an x2. Okay? If he knows x1, he should not be able to find x2. Another word which actually I like a lot is weak collision resistance, schwache Kollisionsresistenz. Okay? And you will know in a second why this is called weak collision resistance, or why it's called collision resistance. Well, we say the two outputs collide. They bang into each other, they're identical. And probably the most important attack, which is really also the motivation for the second half of the lecture, is the third one, which is called collision attack. Okay, and what we require is a collision resistance. So that looks almost the same. Again, we have a collision here in the output, right? The two hash values are the same. What do you think Professor Parr means with this funny notation here? Why do I have two question marks here? What is the difference between this case and this case here? What do you think? Yeah?
I think in the left one, x1 is fixed value, and in the other one, there's random.
Exactly. Right. In the middle, x1 is fixed and given in particular, right? It's just what you say. This is a bank transfer, right? In this right-hand case there, Oscar can choose both values. Okay? So this is called collision resistance. Kollisionsresistenz. Almost the same word in German. Okay? You might think this is completely useless because we need the situation there. But what I want to show you is a collision attack. This was the second pre-image attack or weak collision attack, and now I want to show you a collision attack. Oscar is able to construct x1 and x2 as before. So there's one benign, a gutartige, x1, right, which says please transfer 10 euros into my account. And then there's the malicious one, the fake, the bösartige, which says, transfer 10,000 euros into my account. So let's look how we can map that into a protocol. So we have Alice, Oscar, and Bob as the participants, the actors. Again, Bob sets up his system and sends his public key over, makes his public key public. Oscar, of course, has x1 and x2, again, with those two properties. What Oscar does is he somehow tricks Bob into signing x1. Okay? And that seems far-fetched. How can that happen, right? It's not that I can give you one example would be Bob is Bob, Bob is you or me, is a person. Oscar is a e-commerce house. So he sells stuff on the internet, and this might be the invoice, the bill, right? He says, this is, you bought whatever, new earphones for your iPod, right, for 10 euros. And he says, please pay that and please sign that. This is my invoice, this is my PDF, please sign that and send that to your bank. So what Bob does now is, because X is a PDF and PDF is whatever, 50 kilobytes, so he has to hash that. So he computes the hash value of that, he signs the hash output using his private key. He sends X1 and S over the channel. And again, as is Oscar's chance, he intercepts here. And he replaces this file which says, this earphones cost 10 euros with the message, this earphones cost 10,000 euros. Okay? And again, then Alice is a bank. Alice knows the public key of Bob. So first thing she does, she rehashes. And then she verifies. And she gets a true statement out. Okay. Again, it's a little bit more complicated. I'm not saying this is just the same attack, and it's definitely a little bit more complicated on Oscar's side because he somehow has to trick Bob into doing that, but we can imagine that something like this could happen. Okay? So, these are, and right now we haven't talked about much more, but these are the requirements here, and we should probably put that in a box. They are in the book. Actually, in the book I have a different sequence. A few pages later, you find exactly this listing of requirements here. Okay, so this already ends the second part of the. Now we come to the third one, which sounds kind of the fun thing, birthday paradox, right? But this is the hardest part, okay? So if you slept until now, this is not great, but it's okay, right? You look at these pictures, it's the lecture notes of your body, and it takes you probably 20 minutes to understand what we did in the last 40 minutes, okay? The following part, please pay attention, including row number, 8. Please pay attention with what comes now. This is a cool part too. Okay? It's a little bit mathematics involved. Things are not completely obvious, blah, 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 blah. Please stay awake. Okay? Main part. And we call that collision attacks and the birthday paradox. Nur kleine Frage zwischendurch. Wer kennt das Geburtstagsparadox? Wer hat davon schon mal gehört? It's about 41% of you know the birthday paradox. Okay, so collision attacks are much harder to prevent than second pre-image attacks. So what I'm saying here is there's this one attack. Again, remember x1 was chosen by Bob, and here, and x2 was chosen by Oscar, right? x1 was given by Bob, x2 by Oscar. Here, it doesn't seem all that different, right? x1 and x2 are both chosen by Oscar. It turns out that this attack is much, 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 much easier. When I say much, 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 I mean square root of. You will see that in 20 minutes, okay? So if this takes n steps to do the attacks, this takes square root of n steps. If this is 1 million steps, what is square root of 1 million? Wurzel von einer Million? Very good. So if this is 1 million steps, this is 1,000 steps, okay? If this is 100 steps, this is 10 steps. This is what it boils down to. That means this is a much more powerful attack and which causes a lot of trouble. And I forgot to say that. This is a very, 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 very hot, very current topic, hash functions. Do you remember AES? Does anyone know when AES was created? The year, roughly? 2000, okay? And there was this 3-year process, right? Started in 97, I think. Yeah, 97 was this 3-year process to create AES. The same thing is happening with hash functions right now. They're creating a new hash function. The whole crypto community is working on that. So it's a very cool thing, and this is what we're discussing here. This is a major, major requirement here. So this is very super important. Okay, it's not some kind of odd niche topic that Professor Parr really likes. This is actually, I don't even like it that much, but it's super important. So okay, so the first question. And obviously both attacks are pretty annoying, right? So we don't want to have them. So the first thing that we probably wondering question is, can we have hash functions without collisions? I mean, that should be kind of the normal reaction. You know, we saw 2 attacks. They're not even that complicated here. Okay, so let's build a hash function that doesn't have collisions. And it doesn't work. All hash functions must have collisions. And why is that? Does anyone know the answer? Yeah. Yeah, Bedingung 1 und 2, condition 1 and 2, namely that we allow this is our input space, we allow arbitrarily many, I couldn't even, close that because it's infinitely many, but let's just for visualization pretend I could do that, okay? So if this is the input space, the output space, let's call that the hash space if you wish, where my z values live, right? And what I do is I carry them over, right? I do this mapping here. This is smaller. Okay, and this is a counting argument, an Abzähl argument, right? Let's say we have, give me a number here. Let's say in practice this is 2 to the 160, which is huge, right? But as soon as I have if this has a size of 2 to the 160 plus 1, I must have at least 1 collision. Is this clear? Yeah. So fancy term is, so we have, since x is much, much larger, this is the x space, this is the cardinality, the size of the input, much, much larger than the size of the output space, we must have collisions must exist. What I learned when I wrote the book, there are two very fun, very nice names for this. This is super trivial. This is clear. There's no deeper math, right? Bigger than this, so we must have collision, period. But they're very fancy terms for that. There is the this is either called Dirichlet'sche draw principle. Dirichlet'sche Schubladenprinzip. I think he argued with socks, with Socken, right? If you have 10 socks and you have only 9 drawers, 9 Schubladen, you're going to have a collision, right? There must be one drawer with 2 socks. Everybody with me? Okay. There's a funnier name to it too. Okay. The other one is called the Taubenschlagprinzip. Okay, which is the English word. I have to look that up. This is the Pigeonhole Principle. Okay. Any Taubenzüchter here? Anybody who has pigeons at home? What? Is there anyone? No. Okay. So it's the same. Let's say you have 20 pigeons, but only 19 boxes where they live, right? You must have one box with at least one box with 2 pigeons. Everybody with me? Okay. So this is the first thing that we consider. Since they always exist, one thing is that we could do is that this is really bad. This was a very entertaining 45 minutes. It doesn't work, right? Because you can always find a tag. But this is not true. Don't give up that easily. So the next best thing we must do in our conclusion is that we must have a situation so that we must make collisions very hard to find. Okay, this is the quest. This is the challenge. This is the Herausforderung. Okay. So let's look at how would we actually do such an attack. Okay, so we look at this scenario here. Okay, given is x1, Oscar puts this in a database, and what Oscar would like to have, he would like to find a colliding x2 here. So what he does is, and this is transfer 10 euros, so what he does is he constructs a message which says transfer 10,000 euros. He hashes that, and what he has to check is whether they are identical. Right? This condition up there must be fulfilled. The chances are pretty low, probably, it has to do with the bit length here, right? If you have n bits here. Probably it doesn't work, okay? So you could say, it doesn't work, it's safe, but what Oscar could do is he can construct an x3, and now he can do a lot of things. One thing is, he said, okay, I don't want to have an attack that maps to, where the semantics, the contents is 10,000 euros, but maybe 9,909 euros. That would be one way that you can do it. But he could do even nicer things. He could keep the same semantics, the same context, saying, please transfer 10,000 euros, And at the end of the message, the end of the PDF, he adds one space, one Leerzeichen. You know what I mean? So you add, which is invisible to the bank, right? For the bank, its semantics are the same. However, if you have an additional ASCII character, you feed that into your hash function, you get a completely different output. Okay? You can check whether that works. If this doesn't work, he takes the next one, and so forth. Right? And this is very realistic. Very often you can take a message and you can do variation at invisible positions, really. Or you can add tabulatoren, tab stops. You can do all kind of things typically to message that you don't see. Or if you have a encoding with 7-bit ASCII and you use the 8th bit of each character is not used. So each character, every character of your text, you have kind of one extra bit, and you can either set that to 0 or 1. That means with the same meaning, saying transfer 10,000 euros, you can generate many messages, and you can try to find a collision here. Okay? If, let's say, that if the cardinality is 80 bits, not 160, that means we haven't, this is 80-bit output here, then attack requires 2 to the 80 steps. Okay? Every time we have a new input, we get a pseudo-random output, pseudo-random 80 bits, and you have to run that roughly 2 to the 80 times until you find a collision. Okay? So what we're going to do now is we try to do the same thing. The same thing with the collision attack. Okay. So this was preimage. Now we do collision attack. Okay. So it turns out that this is closely related to this problem of, let's have a party, and how many people do we have to invite so that 2 people have birthday on the same day? Seems very weird. Okay, we have a party, and maybe, and what preimage tells us, if you have a preimage birthday collision, what that would mean, my birthday is July 18th, okay, and the question would be, how many people do I have to invite so that there is at least one other person who has his birthday on July 18th? What do you think on average, how many people do I have to invite? What is your gut feeling? You're all engineers. Any ideas? And on average, I mean, I could have bad luck. I could invite 1,000 people, and none of them has, has birthday on the July 18th. But on average, what do you think? Yeah. No. Much more. Yeah. How much?
200.
No, 200 is good. Yeah. Close enough. About 180. Why is that? With everybody coming in, I think it's half of 365. This is what I need to do. Okay. And this maybe what we kind of expect. If you're coming in, you have this one chance of hitting it right. So on average, I need 365. Right? Is that all right? Yeah, on average I need 365 people, so big party, okay? On average I need 365 people to have that. Again, I could be lucky, the first person walks in and I said, oh, July 18th, right? We have a collision. I could have 1,000 people who don't have July 18th birthday, but on average it's 365. So it turns out if I slightly change the requirement, I said, I want to have 2 people that collide with the same birthday, but not July 18th, but any day of the year. Okay? And what we do is a little bit experiment. I'm handing this sheet around, okay? You put down your birthday, not the year, okay, day and month. It's very easy. I'm not going to explain that. And as soon as we have a collision, jump up and yell, okay? And then we start here, okay? So as soon as you have a collision, say... And don't worry about the sheet. Look to me, okay? So... And now we're trying to do the math. I know this is really fun and exciting, but calm down, okay? So what is the likelihood that we start with a small party? It's me and one guest. So what is the chance that this one guest also has birthday on July 18th? Exactly this, right? Pretty small likelihood. Okay. The chance that he collides with me is 1 over 365. Chance that he not collides is 1 minus that. Okay. So what is the chance if you have 3 people? And now wake up. Now it's the most important sentence of the whole 90 minutes. Alle wach, hallo. Most important sentence. So we have 2 people, okay? The third person enters. This third person has now choices. This person can collide with me or with the second person that's already in the room. Okay, that means the probability changes here. This is a chance that the first person collided with me. The second person has much more choices. Second person can have this likelihood. Okay. If we continue that, and let's look what happens if you have T people, T Person. What we get is this likelihood. Do we have a collision yet on the paper? No. Start yelling, okay, if you're there. Okay, so it turns out for T equals 23, so that means if you have 23 people in the room, we get P of the pi symbol running from 1 to 22. We have a 50% chance this happening. Okay? And that's a birthday paradox. This is not 365 anymore, it's 22. Okay? And if you do the math, this is roughly the square root. Okay? So now we're going to talk more into that. What's happening cryptographically speaking is we start here. And if the attacker constructs the first message, he has only one possibility to collide. If you construct the second message, before you could only compare it with the first one, but here you can compare it with this and with this. If the attacker constructs the third message, he can check with all the previous ones. Okay, you get a feeling just the number of collision checks that I draw grows exponential here. And now let's try to derive an expression for a hash function. Do we have a collision? 9? Okay. Should be 23 people roughly, okay, so. So this is the situation with respect to hash functions, okay? We have x1, x2 up to xt, and we have one output here, okay? Again, what you start with, P of no collision with T input values is again this pi symbol here, this Produkt symbol. And before 365 was the output space here, okay? What is the output space here? Before we had 365 possible outputs, all the birthdays of the year. How many output values do we have here? Does anyone know how big is the Z space here? How many possible Z messages do we have? Yeah. 2 to the n, exactly. Very good. Very, very good. Okay. So, look in the book, blah, 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 and at the end you get the following very, very important formula out. What does this formula tell us? This is the most important formula of the lecture. And first, what are the symbols? T is easy. T is the output of the number of inputs you have to feed in the hash function. This is, you don't know that yet, this is probability for at least one collision. Example, if you have 80 output bits here, which was actually, by the way, 80 output bits were sufficient for a second pre-image resistance. Now let's assume we have 80 output bits. And we want to have a 50-50 chance of a collision, okay? If he plugs that into the formula, yeah. I forgot the Wurzel, yeah, okay. Most important part, very good. If I plug these numbers in here, do we have a collision? Haben wir eine Kollision? No? So keep going here. The colleague is going to continue. So this is the end here. What does this tell us? Before, with the collision attack, even if you have an 80-bit output, so it seems like we have a security of 2 to the 80, but it turns out we only need 2 to the 40 values to find a collision. Okay? So you get the square root in here. Okay? That means a collision, that means in order to get 80-bit security, we need twice the bit length. We need 160 bits of output length at this point here. Okay? We're going to talk about much more about this next week. That's the end. Now the colleague is coming, and please stay. Thank you very much.